advantages, if one can call it, of this COVID pandemic, that we all have started thinking about how to get people together over video. And because of that, we can have a lineup of speakers from all over the world and just share their knowledge to with everyone. So it's a wonderful start. I would like to congratulate all the organizers of this event. And I'm very sure that the participants will learn a tremendous amount of mathematics in this series. All the best. Thank you.
Thank you very much for your inspiring words and for your valuable time, Professor Agarwal. Now it is my great pleasure to introduce Professor Sandeep Kunath from Tata Institute of Fundamental Research, Center for Applicable Mathematics, as the first speaker of this webinar series. Professor Sandeep Kunath's research interest lies broadly in the areas of partial differential equations, variational methods, and nonlinear function analysis. He is the recipient of prestigious Shanti Swarup Bhatnagar Award, the highest science award in India. Currently, he is the Dean of TII for CAM. Today, he will give a talk on Ritz kernel type estimates and Adams inequality. I hope you will enjoy his talk thoroughly. Sandeep, it's over to you now.
Okay, thank you, Prasanjit. Yeah, is it visible now?
Yes.
Okay, can I start?
Yes. Sandeep, you muted now. Can you unmute yourself? Ask to unmute.
It's fine, right?
Yeah, it is fine. It is fine.
Okay, yeah, fine. Okay, so thank you, Prasanjit, and all the members of the organizing committee for inviting me to give this talk. So I'm going to talk about Ritz kernel type estimates and Adams inequality. Okay. So the plan of the talk is I'm first going to explain you what this inequality means, Adams inequality, and what is the role of Ritz kernels in these inequalities. And then after that, I will try to explain some of these results I have proved recently on Riemannian manifolds. Okay. So the first I will try to introduce this inequality. Okay. So let me start with So let me start with the well-known Sublevel inequality. Okay. So all the people who works on partial differential equations know this Sublevel inequality. So let me recall once again. So the well-known Sublevel inequality says that let 1 less than or equal to p less than n, where n is the dimension of Rn, the Euclidean space Rn, then there exists an optimal constant Snp greater than 0, such that the following inequality holds, that is Snp into integral over Rn mod u to the power p star all to the power p by p star is less than or equal to integral over Rn modulus of gradient of u to the power p dx. This holds for all u in CC1 of Rn, where p star is equal to np by n minus p. Okay. And in fact, you can show that if you put instead of p star any number q and different from p star, then the inequality does not hold. And p star is the unique exponent for which this type of inequality holds. Okay. So this basically tells you that for functions, so the LP norm of the gradient, which controls the LP star norm of the function u. Okay. And p star is unique, and this is going to be the form of p star, which is given by np by n minus p. And as I mentioned before, you can show that p star is the only exponent for which this inequality is possible, which can be easily seen by using a dilation argument, in the sense that if this inequality holds for a function u, then I can define another function u of lambda x is equal to u of lambda times x for a positive number lambda, and then you plug it, and then you can take lambda goes to 0 or infinity, and you will see that it is not possible. Okay, so it's possible only when p is equal to p star. Okay, So I have this condition that 1 less than or equal to p strictly less than n. That makes that this p star is positive real number. And also as p goes to n, p star goes to infinity. Okay. So I also want to, for future purpose, I also want to rewrite this inequality in another form. For example, you can normalize on the right-hand side and you can assume that to be 1. And then the inequality takes this form. Equivalently, you can write this inequality in the form supremum of u in CC1 of Rn, integral over Rn, gradient of u to the power p is less than or equal to 1, integral over Rn, mod ux to the power p star dx is less than or equal to SNP to the power minus p star by p. So this SNP is the same what I have written here. Okay, so these two inequalities are equivalent, and this is the form which we will be using in future. Okay, so please observe that this inequality most of the time we will be considering like this. Okay, so this inequality is for the case p less than n. Now the question is, what happens when p is greater than or equal to n? Yeah, before that, so this SNP, I wrote here that there is an optimal constant. So in fact, you know the explicit value of that constant. This SNP has an explicit form, which is n into n minus p by p minus 1 to the power p minus 1. And you have this one more term here. Okay, so that's the explicitly known. This constant is explicitly known, and the result is attributed to Rodimich, Oban, and Talenti, and so on. Okay, so one of the important thing which you notice here is that when p goes to n, this SNP goes to 0. Okay, note that SNP goes to 0 as p goes to n. And one disadvantage of that is that in this inequality, if since SNP goes to 0, when p goes to n, this goes to infinity. Okay, so when you are trying to take the limit as p goes to n, this inequality is basically doesn't contain any information. Okay, so we cannot get any information about this type of inequality when p is equal to n from this. Okay, and so however, when p greater than n, we have another inequality, what is known as the Morris inequality, which tells you that this gradient of u to the power p, it controls the Helder norm of this function. Okay, so there exists an optimal constant SNP for p greater than n, such that this inequality is valid when p greater than n. So, or in other words, it tells you that when p is greater than n, the gradient of u to the power p, that is going to control the Helder norm of the function. Okay, so in terms of the Sobolev embedding theorem, for those people who know about it, it says that when p is less than n, you have a control over the LP star norm. When p is greater than n, you have a control over the Helder norm of the function. So the main question we are interested in this talk, what happens when p is equal to n? Okay, as I mentioned before, we cannot take the pass to the limit as p goes to n in the inequalities which I have stated. Okay, so we cannot pass to the limit as p goes to n in the above inequalities. So now the question is, can we do something better? So that is where you recall, I have written the Sobolev inequality. Let me go back and see here. So I had an inequality here, which I have written here. Okay, so here, this Sobolev inequality tells you that you have mod u to the power p star. Okay, that is controlled. So the question is, can you replace this mod to the power p star by another function which is better than a polynomial, or mod u to the power p star? Okay, so that's precisely the question that I'm asking here. Can we have an embedding of the form this one? Okay, that is supremum over u in CC1 of Rn, integral over Rn, gradient of u to the power n less than or equal to 1, integral over Rn, phi of ux dx, that is less than or equal to some Cn, which is finite, for a phi growing faster than polynomial power at infinity. Okay. So the question is, can we have this kind of an inequality? Because as p goes to n, we saw that that constant goes to 0. So we cannot control the L infinity norm. In fact, you can show that it is not possible. It's not only that Pn goes to 0, you cannot control the L infinity norm using the Ln norm. Okay. So now this is one option that we have. And can we have this type of an inequality? So there is a theorem. It's a result of what I'm stating is a result of Schrodinger, who proved that let omega be a bounded domain in Rn, then W01n of omega is continuously embedded into L phi star of omega, where L phi star omega is the Orlik space defined by the function phi of t is equal to e to the power mod t to the power n by n minus 1 minus 1. Okay. So let's not bother about what this Orlik space is. I will state in a few seconds what exactly it means in terms of inequalities. Okay. So whatever I stated before, the embedding, that is actually equivalent to this statement. Okay. So it tells you that there exists a constant alpha and c positive such that integral over omega e to the power alpha mod u to the power n by n minus 1 minus 1 dx is less than or equal to c, which is finite. This holds for all u in cc1 of omega, satisfying integral of omega modulus of gradient of u to the power n plus mod u to the power n dx is less than or equal to 1. Okay. So the result is attributed to Schrodinger, and some portion of the results or somewhat were proved by Poisson and also by P3 around the same time or almost at the same time. Okay. So one of the motivation for Schrodinger to prove this type of an inequality was that he wanted to have a proof for the well-known Moser's Harnack inequality, avoiding the BMO estimate. That means the exponential integrability of BMO functions estimates. So he wanted to avoid that, and he wanted to write an independent proof, and that was his idea, and he proved this, and using that he completed his program. For details, you can see his Schrodinger's paper or the book of Gilbert and Schrodinger, where this program is carried out in full detail. Okay. So so we have such an inequality. And also there was works by Schrodinger and his collaborators, which tells you that in this inequality, if you look at this power n by n minus 1, that is the optimal power you can have. Or in other words, if you replace this n by n minus 1 by another number p, which is bigger than n by n minus 1, then this inequality is not true. Okay. So if at all you want to have an improvement of this inequality, that is about this number alpha. So this Schrodinger's result tells you that there exists an alpha positive. So you may wonder, can you have an optimal choice for this alpha? So in fact, Moser was in need of such an optimal constant when he was studying the problem of prescribing the Gaussian curvatures or Sn in a conformal way. Okay. So I'm not going to the details of what the problem is. Moser was in need of finding the best constant its inequality, and he studied that problem, and he in fact invented what is the best constant in this inequality. Okay. So let me state that theorem, which is due to Moser, who proved that there exists a positive constant C0 depending only on the dimension, such that this quantity supremum of u element of cc1 of omega, and with the constraint integral of gradient of u to the power n less than or equal to 1, then you have integral over omega e to the power alpha mod u to the power n by n minus 1 dx is less than or equal to C0 into measure of omega. So this inequality holds if and only if alpha is less than or equal to alpha n. There is a dimensional constant alpha n, which is given by n into omega n minus 1 to the power 1 by n minus 1, where omega n minus 1 is nothing but the surface area of the n minus 1 dimensional sphere in Rn. Okay. So he showed that alpha, and not only that, he showed that if this alpha is bigger than this alpha n, then this supremum is going to be infinite. So, or in other words, the best constant in this inequality is this number alpha n, which is n into omega n minus 1 to the power 1 by n minus 1. Okay, so this constant is sharp, and that is what was the result of Moser. And this inequality is the inequality what we call today as the Moser-Trödinger inequality. So in future, when I refer Moser-Trödinger inequality, I mean this type of an inequality with the optimal constant here, alpha is equal to alpha n. For example, when n is equal to 2, this alpha n is going to be equal to 4 pi, just for your information. Okay. So let me just tell you a few words about the proof, how Moser proved this inequality. So the main tool which he used is what is known as the symmetrization. Okay. So using symmetrization, you can actually reduce this problem to proving this inequality in the case when omega is a ball and u is a radially decreasing function. Okay. And then you can do some change of variable, and then you end up proving this kind of a one variable inequality. So let me just read out this inequality. So Moser reduced, using symmetrization argument, he reduced the inequality to a one variable inequality, which is as follows: let 2 less than or equal to p less than infinity, 0 less than beta less than or equal to 1, and 1 by p plus 1 by q is equal to 1. Then there exists a constant which depends only on p and beta, such that this inequality holds for all C1 functions defined on 0 infinity to 0 infinity, satisfying w0 is equal to 0, w prime is greater than or equal to 0, and integral 0 to infinity, w prime t p dt is less than or equal to 1. Okay. And so the problem reduces to one variable. That doesn't mean that the problem becomes simple, but still it makes the life simpler. And Moser did manage to prove this one variable inequality, and hence the result. Okay. So that is how he proved this result. Okay. So this was the case when I talk about the first order Sobolev space, or what I mean is that the term involved in here is only the first order derivative. Okay. So now the question what I am interested is, what about the higher order derivatives? Okay. So for k is equal to 1 or the first order, I had the gradient. So let me define the higher order gradient as follows. For k in n, kth order gradient I will define as, it is like Laplacian to the power k by 2 if k is even, and gradient of the Laplacian to the power k minus 1 by 2 if k is odd. So be careful when k is even, Laplacian kth order gradient of u is a function, and when k is odd, it is going to be a vector. Okay, it's a vector valued function. So this is how we define the kth order gradient. And then what happens is that, like we had a Sobolev inequality when p is less than n. When you have a higher order gradient, we have the Sobolev inequality with the right hand side as integral of kth order gradient to the power p when kp is less than n. You can see that when k is 1, this is exactly becomes p less than n. Okay. So when k is greater than 1, the condition p less than n reduces to kp less than n. So like in the case of Moser-Trödinger, where p is equal to n, in the higher order case, the case which we have to deal with is the case kp is equal to n. So that's the question which I am asking. What about the case when kp is equal to n? Okay. So Adams proved that similar to Moser-Trödinger inequality, you have a very similar inequality in this case. Okay. So let me read out this what Adams proved this inequality. Let 1 less than or equal to k less than n, where n is the dimension of the Euclidean space. There exists a constant which depends only on k and n, such that supremum over u in cck of omega, this kth order gradient, the pth power is less than or equal to 1, integral over omega e to the power beta times mod u to the power p dash dx is less than or equal to c0 into measure of omega. This holds for all beta less than or equal to an optimal constant beta naught. Okay. So where here I take this p as n by k, or in other words, p into k is equal to n. Okay. So that is the relation between k into p is equal to n. When it is less than n, we have the Sobolev inequality. And what we are interested is in Kp is equal to n. And this P dash is equal to is the conjugate exponent P by P minus 1. Note that when P is equal to n, it was n by n minus 1. That's exactly what we saw in the case of Moser-Schrödinger inequality. Those inequality looks very similar and in the same way. And this beta naught Kn is an optimal constant where he has computed it, what it is. And I'm not expecting anybody to remember this, but the only thing is that in future, whenever I write this beta naught, please remember that it is the optimal constant in this Adams inequality. So I will just use the term beta naught Kn in future when in other contexts, and it means that this constant. Okay. So again, here also like Moser-Schrödinger, he has proved that when beta is strictly greater than beta naught, then the supremum is infinity. So in other words, this beta naught is the optimal inequality. Okay. So now what is the difference between Moser-Schrödinger and Adams inequality? So I already told you that Moser-Schrödinger, Moser proved the optimal form of this inequality by reducing it to a one variable inequality using symmetrization. But the main difficulty, and in the process, what we have to use is an inequality known as the Polyacicos inequality, which tells you that basically you take the LP norm of the gradient and the symmetrized function. In fact, the symmetrized function decreases the gradient. Okay. So for higher order gradient, when k is greater than n, such Polyacicos type inequalities are not available. And that is the main obstruction for proving the Adams inequality. So let me briefly explain how Adams proved this inequality. Okay, so that is where the next word in my title, that is the Riesz potentials, comes into picture. Okay, so the plan of Adams proof was basically, I can divide into basically 3 steps. Let me go to the first step. Okay, so the first step is the Riesz potential representation. Okay, so the first thing I am going to write is I am going to write U as a convolution of the kth order gradient against a potential. Okay, so you can see that when k is odd, it is k minus x minus y by mod x minus y to the power n plus 1 minus k. And when k is even, then you have this. Okay, so it's basically your Riesz potential, and where you have this explicit. Okay, so you have this explicit representation for these functions. Okay, and I can even put it in a much simpler form by reducing all these, introducing a notation. I can write that I can take a modulus in U, and I can write that mod U is less than or equal to the same constant Ckn, that into I alpha convolution, this kth order gradient of U, where I alpha is the singular exponent, singular function, mod x to the power alpha minus n, with alpha is equal to k. Okay. So I have a representation of U in terms of this kernel with I alpha, and I am convolving with gradient of kth order gradient. So notice that in the inequality, you see this LP norm of the kth order gradient comes, and U is coming here. So with that adjustment, what happens is that you are going to represent this U using the given quantity, that given constraint, that is the LP norm of the gradient. Okay, or in other words, with this representation, I can reduce, or Adams reduce the problem to the following convolution type estimates. Okay, so what he proved is that, so you can just rewrite this inequality in terms of convolution. So what you can prove is that the problem reduces to, let omega be an open set in Rn with a measure of omega is finite and 1 less than p less than infinity. Then there exists a constant Cp greater than 0 such that the inequality integral over omega e to the power n by omega n minus 1 into modulus of I alpha convolution f to the power p dash dx is less than or equal to Cp into measure of omega. This inequality holds for all f in Lp of Rn with LP norm less than or equal to 1, and support of f is contained in omega, where alpha is going to be n by p. And moreover, this constant n by omega n minus 1 appearing here is the optimal constant in the above inequality. Okay, so the first step is just he rewrote the inequality, the Adams inequality, whatever he wanted to prove in terms of this convolution type inequality. Okay, so but it's only a way of writing it, and the problem reduces to proving estimates on the convolution inequalities. So, but that again doesn't make the problem one-dimensional. Okay, it's still a problem on several variables. Now, how do you get the reduce the problem to one dimension? That is what I wanted to estimate. Okay, so all of us knows that if you wanted to integrate a function, one way is to convert. You can integrate it in terms of the distribution function. Okay, so let me just recall some of these tools. You have a measure space and you have an f from x to minus infinity to plus infinity. Then you have the distribution function f, lambda f, which is given by lambda f of t is equal to measure of set of all x, etc. Mod f is greater than t. And its non-increasing rearrangement, f star, I will define as follows. F star of t is equal to infimo s, such that lambda f s is less than or equal to t. This you can define for all t positive. Okay, so you can see that, for example, if lambda f is a, you can see in some sense as m star is going to be an inverse of lambda f. And f star star t we define as the average 1 by t integral 0 to t f star of s. And with these notations, I can tell you how to calculate these kind of formulas. I will just write down the expressions. So with those expressions, integral of mod f to the power p, it becomes a one variable integral. That is 0 to measure of omega f star to the power p. So f star is a one variable function. You convert here. And in the second one, the quantity what we are interested here, okay, and that converts into this type of an inequality. Again, it is a one variable inequality, and it becomes like this. Okay, so what we have is a rearrangement of I alpha convolution f. Okay, so but again, I alpha is a known function, so you can calculate its rearrangement. F is the given function, you can have its rearrangement, but I alpha convolution f, still the difficulty lies here. Okay, even though the problem became one dimensional, still there is a difficulty here. And the crucial tool Adams used is inequality of O'Neill. Okay. So what is known as the O'Neill's lemma, which tells you that how to calculate this f star g, the double star t, is you have this formula. Okay, so the convolution f star g, and you can find this double star of that you can write in terms of f and g. That simplifies the problem to a great extent in calculating this quantity, because I alpha, double star, etc. you can calculate very easily. And then using that, Adams reduced the problem to a one variable integral as follows. Okay, something like what was in the theorem of Moser. He reduced the problem to a one variable inequality. It's ended up with proving a one variable inequality, like there exists a constant Cp greater than 0, such that integral 0 to infinity phi to the power p ds less than or equal to 1 implies 0 to infinity e to the power minus ft dt less than or equal to Cp, where f is given by this kind of a function. Okay, still there is a lot of work needed to prove this, but the problem is one dimensional, and there were already some works in this kind of direction, and Adams was able to adapt those existing works to his situation, and he is able to prove that inequality. Okay, so that was basically the approach of Adams. So the key point I want to emphasize again is that the first step in Adams' proof was to reduce the problem to represent the function as a integral against a kernel. Okay, and then you have the proper estimates for that, and you see the O'Neill's inequality and reduce to a one-dimensional inequality and prove this inequality. Okay, so now the main topic which I wanted to discuss today is about this inequality on Riemannian manifolds. Okay, so my focus will be on non-compact Riemannian manifolds. Okay, so first let me briefly recall what is known in the case of compact Riemannian manifold. Okay, so in the very first work of Moser, which I mentioned in the beginning, where he established what we call today as the Moser-Totinger inequality, in the same paper, he has introduced a similar inequality on S2, that is the two-dimensional sphere. In fact, that is what he was needed. He was in need to prove to study the question of prescribing the Gaussian curvatures on S2 in a conformal way. Okay, so he had an inequality in that. I'm not going to state it explicitly here. It's lack of time. And then this is about the Moser-Trödinger, and about the Adams inequality on compact and manifold. It was established by Fontana in 1993. Okay. So I just want to make few remarks here. Again, Moser's proof on Moser-Trödinger inequality was using symmetrization. So what he did was that the symmetrization tools were available on S2, and using that he converted the problem to a one-dimensional, and he proved this. And this Fontana's proof was after this Adams result on the Euclidean space. What he did is that he adapted the tools of Adams in the Euclidean space to compact manifold, and then using this kind of a potential approach, and he proved the inequality. Okay, so the only difference is that when you come to a manifold, you won't have this kind of a representation. So let me go back, and yeah. So here I have this kind of mod u is less than or equal to I alpha convolution this. Okay, so when you go to a manifold, you may not have a convolution structure, but instead of that, you will have something like a mod u is less than or equal to integral of some kxy into gradient of that. So it will be, it may not have a convolution structure, but it will be an integral against a kernel. So that is what we have to deal with. Okay, so that was the case in the case of compact Riemannian manifold, and Fontana managed to establish this inequality on the compact Riemannian manifold. So now, as I told you, yeah, so let me just state what exactly Fontana has proved in the case of compact Riemannian manifold. So the inequality is the following: let Mg be an n-dimensional compact Riemannian manifold and 1 less than or equal to k less than n. Then the Adams inequality, you have the same type of inequality whatever you had in the Euclidean space, okay, where omega is replaced by a compact Riemannian manifold. And it says that this inequality holds if and only if beta is less than or equal to beta naught. Beta naught is exactly the optimal constant. We have it in the Euclidean case. Okay, so here the only observation you have to make here is that there is an extra condition here, that integral of u is equal to 0. This is needed because the manifold is compact. Therefore, if you take any u, you can add a constant to that. Or in other words, you just take a constant, any constant, say an integer, k is equal to some m. Gradient of k of a constant is 0, okay? And but e to the power beta into n, and that will go to infinity. So you have to kill those constants. So you have to have an extra condition. So the condition which Adams introduced is in this form, that integral or m u is equal to 0. So this is the extra condition which you will impose when u comes to compact Riemannian manifold. And so the proof was more or less in the spirit of the Adams, using the potential approach, writing the function as an integral against a kernel. Okay. So now let me go to the main topic of my lecture today. So my result, and that is on the non-compact manifold. Okay. So yeah. So I'm going to talk about the case of a non-compact Riemannian manifold. So let me start with, let Mg be an n-dimensional complete non-compact Riemannian manifold, and let me denote by mu g the corresponding Riemannian measure or the volume. Okay. Then there are standard arguments. Using that, you can show that on a complete non-compact Riemannian manifold, if you have Sobolev inequality, then the volume of the manifold has to be infinity. Or in other words, if you have a complete non-compact Riemannian manifold with finite measure, then you cannot have the Sobolev inequality. Okay. So in fact, with very little effort or little modification, you can also prove that the same conclusion has to be there if you need a Moser-Trödinger or an Adams inequality. Okay. So if you need to prove some kind of Sobolev embedding or Moser-Trödinger or Adams, so you better assume that the manifold is of infinite measure. Okay. So that's what the assumption I am making. Assume our manifold is complete, non-compact, and measure is infinite. Okay. So now, as soon as you put this measure is infinite, then you immediately see that integral of m mod u to the power p d mu g, this is infinity for any u, because e to the power mod u to the power p, this quantity, independent of what u is, it is always greater than or equal to 1. Therefore, this integral is always greater than or equal to the measure of the manifold, which is infinity. Okay, so we cannot expect a Moser-Schrödinger in this case, or Adams inequality in this case, like what we had before, just by keeping this function. So one way is to modify this exponential function. So that's what I'm going to do first. So we modify the exponential function as I define of es of x for a natural number s. Es of x is equal to e to the power x minus sigma I equal to 0 to s minus 1 x to the power I divided by I factorial. Okay. So, or in other words, es to the power x, the first term in the expansion of es to the power s is x to the power s by s factorial. Okay, so the 1 doesn't appear there anymore when s is positive. Okay, so and you can also see that es to the power x is greater than or equal to x to the power s by s factorial. Okay, so so the hope is that can you replace this exponential divided by replaced by this kind of a function, and can you prove such an inequality so that this kind of an obstruction is not there? So that is a question, that's what I'm asking. So can we look for inequalities of the form? The same thing here, supremum u is on cck of m, and then I have the kth order gradient of u. I take the pth power and less than or equal to 1. The constraint is as before. And then instead of exponential, I replace it with es. Okay, and I put this condition, and then the question is, can you say that it is less than infinity? And such that this holds for all beta less than or equal to beta naught of kn. Okay, so that is the question, that the modified question that we are going to ask on the non-compact Riemannian manifold. Again, let me stress that this beta naught is again the same constant which is appearing in the Adams inequality in the Euclidean space. Okay, so first let me make some observation. Suppose you have this kind of an inequality, then immediately it will have some consequences. As I told you before, es is greater than or equal to x to the power s by s factorial. So so that means es is bigger than x to the power as a polynomial power. So if this quantity has to be finite, then if you replace es by a polynomial power, then still it has to be finite. Or in other words, if this inequality has to be true, then it will immediately imply that you have to have inequalities of this form. Okay, so the observation is that if I have Moser or Adams inequalities like what I have stated before, then we should immediately have inequalities of this form. Okay, that means this is kind of a Sublevel inequality. So we can hope to prove this Adams inequality of the type which I mentioned on a complete non-compact Riemannian manifold if and only if it admits some Sublevel inequalities of this form. But this is not that obvious, and manifolds may not in general admit these type of inequalities. For example, the Euclidean space is the example. When m is equal to Rn, you can show that using the scaling arguments, we can show that such inequalities are impossible as Kp is equal to n. Kp I mean is that k into p is n. You can see that this inequality is not possible in the Euclidean space. Okay. So what is the alternative in the Euclidean space? People have overcome this difficulty, or what you can do is that instead of the constraint here, however, in this case, we can prove the embeddings if one replaces the constraint integral over m gradient, the pth power of the kth order gradient divided, you replace this by adding one more constant. You have to put the LP term as well. You replace that, then you can have the inequalities. In fact, there has been many inequalities which are proved in the Euclidean space with this kind of an assumption. Okay, so there are plenty. I don't have the time to mention any of these inequalities. Okay, now, so I mentioned this inequalities, and I told you that in general. So if you want to prove this Adams inequality, you better look for manifolds where you have sublevel inequalities. So one of the manifold in which you have plenty of sublevel inequality, like in the Euclidean space, is the Cartan-Hadamard manifold. Okay, so that's what I have written here. A class of non-compact manifolds where we have the sublevel embedding is the Cartan-Hadamard manifold, which is nothing but a complete, simply connected Riemannian manifold with non-positive sectional curvature. Okay, if you are not familiar with this terminology, it is just the Euclidean space Rn, but with a different metric. The only thing is that the metric, the curvature has to be the less than or equal to 0. So the important examples for the Cartan-Hadamard manifolds are Euclidean space, hyperbolic space, and so on. Okay. So in these Cartan-Hadamard manifolds, we have plenty of sublevel inequalities. So let me just recall some of these inequalities. And the first and foremost, we have the sublevel type inequalities on Cartan-Hadamard manifold. So let Mg be an n-dimensional Cartan-Hadamard manifold and 1 less than or equal to p less than n, then you have this sublevel inequality. This is the corresponding inequality what I stated in the beginning in the Euclidean case. The same thing is true even in the Hadamard manifold. Okay. So now if you impose further conditions, what you will see is that you can even have Poincare type inequalities. That's what I am going to tell you now. See, the Cartan-Hadamard manifold means the sectional curvature is less than or equal to 0. But if you need Poincare, if you can have Poincare inequality when you demand that the sectional curvature is strictly negative. Okay, so that's what I am stating next. So this is a theorem due to McKean for p is equal to 2 and generalized to for general p by Strickhartz, which tells you that if you have a Hadamard manifold with a sectional curvature less than or equal to minus a square, which is strictly less than 0, and then you have this Poincare type inequalities. Okay, and not only that, these constants are the best constant in these inequalities. Okay, so these are the best constants, so you cannot improve this constant. But the only thing is that you need the curvature to be strictly less than bounded away from the origin. Okay, so you know that when it is equal to 0, for example, in the Euclidean space, you cannot have Poincare inequality. Okay, so this is expected. You need some extra condition. Of course, there are conditions. If you don't have strict inequality, you have to impose some further condition. There are results like that, but still, this is one thing which we can easily state here. Okay, so now when we talk about the Adams inequality, I have been talking about the kth order gradient. So that means I require inequalities where instead of this gradient of u, I need kth order gradient. Okay, so in fact, we have such inequality, but we need to put an extra condition. Okay, so what it says is that Mg is a Hadamard manifold with sectional curvature less than or equal to minus a square. And the extra condition I require is that Ricci is bounded from below by minus p square. Then you have this kind of Poincare type inequalities for higher order gradients. Okay, and here you have this inequality, and I refer to one of our recent papers for a detailed proof. And the only thing which I wanted to tell you is that it's basically you have to prove this result for k is equal to 2. After that, you can iterate the argument. Okay, and the basic thing is that let Mg be a complete Riemannian manifold satisfying this Ricci greater than or equal to minus n minus 1 b square, and whose spectral gap is positive. So in fact, in our conditions, sectional curvature is less than or equal to minus a square. That gives that there's a spectral gap. Then you can actually show that this kind of an inequality holds. Okay, and this is basically what goes into that. And that basically comes from the kind of a multiplicative inequality like this, which holds on any complete Riemannian manifold. And then you need another inequality, which basically an estimate on the boundedness of the Riesz transform. And for that, you need the boundedness from below of the Ricci curvatures. Okay, I'm not going to the details because of lack of time. And I refer to our paper if you are interested in more details about this. Okay, so the main thing I want to stress here is I have this kind of a Poincare type inequalities under the two conditions. You have the Hadamard manifold. Sectional curvature is bounded from above minus a square and Ricci bounded from below by minus a square. Okay. So then you have this inequality. And then what about this Moser, Trödinger, and Adams inequalities on this Cartan-Hadamard manifolds? Okay. So I told you already that the important examples of Cartan-Hadamard manifolds are Euclidean space and hyperbolic space. And we already described the results in the Euclidean case. And in the hyperbolic space, there are results available. For example, the Moser-Trödinger in the hyperbolic space was proved by me and Mancini way back in 2010. Okay, so and the Adams inequality in the hyperbolic space was proved by Karmakar and me again in 2016. And there was also a proof for the Adams, another type of Adams inequality in the hyperbolic space was established by Fontana and Morpurgo. Okay. So the proof of the first one, what I mentioned, and the proof here again, me and Karmakar, both of them depends on the conformal invariance of the hyperbolic space and the Laplace-Beltrami operator. And while the proof of Fontana and Morpurgo, it depends on the conformal invariance. Sorry, it's a Riesz potential approach more in the lines of Adams. Okay. So now the question which I wanted to ask here is, what about the general Hadamard manifolds? Okay. So we indeed proved such an inequality. So it's a joint work with Jerome Bertrand. It's in a recent work. So what we proved is that the assumptions what we require are the following. So Mg is an n-dimensional Hadamard manifold satisfying Kg is less than or equal to minus a square and Ricci is less than or equal to minus n minus 1 into b square for some a and b greater than 0. And let k be an integer satisfying 1 less than or equal to k strictly less than n, and p is equal to n by k, then you have the expected Adams inequality. Okay, so here I was talking about an ES, that S is going to be the integer part of p minus 1. This bracket p minus 1, I mean the smallest integer bigger than or equal to p minus 1. So you have an inequality, and the best constant is this, the same as the Euclidean one. Okay, so this is so we have a general result on the Hadamard manifold. Okay, and the condition which we require is that sectional curvature is bounded from above by minus a square, and so Ricci is bounded from below by minus n minus 1 into b square. Then we have. Okay, so our proof is basically using the potential approach. Okay, in the Euclidean space, as I mentioned, you had the Riesz kernels to represent the function. Here, what do we do? Okay, so I'll briefly explain the method. So we have to develop substitutes for the Riesz kernel and develop estimates. Okay, and when k is equal to 2, the natural candidate is the Green's function. Okay, so let me recall just briefly what a Green's function is. So Mg is a Riemannian manifold, then an entire Green's function of the Laplace-Beltrami operator is the function g from m cross m minus the diagonal to 0 infinity satisfying. Okay, so the Laplacian of gx is equal to 0, or in other words, it's a Dirac delta and so on. And it is symmetric, and also near the singularity, or y is equal to x, it behaves more or less like the Euclidean singularity. Okay, so this is a standard definition of Green's function. I'm not going to the details because of lack of time. And then the general definition. And then you can have this theorem that for a Hadamard manifold, just you take a Hadamard manifold, then it admits a Green's function g satisfying this estimate. So the Green's function is going to be positive, and you have an upper bound of it by phi of dg of x minus y. dg is the distance, the Riemannian distance between x and y, where this phi is the fundamental solution, Euclidean fundamental solutions, what we are familiar with, which is given by this. So basically in the Hadamard manifold, you can control the Green's function from above by the Euclidean fundamental solution, where modulus is replaced by the Riemannian distance. That is the one. And you also have the representation formula. That is what we were interested in. U can be written like this. And recall from the definition that this is nothing but the second order gradient, Laplacian. Okay, so you indeed have a representation for u using the second order gradient here. Okay, and under our conditions, and this Green's function estimates can be even better. Or in other words, what I'm saying is that Mg is an n-dimensional Hadamard manifold. Now I assume that sectional curvature is less than or equal to minus a square and Ricci is greater than or equal to minus n minus 1 into b square. Then you can improve the estimates on the Green's function. Then you can control from above by a quantity like psi a of dg of x minus y and psi b of dg of x minus y, where psi a is this kind of a function. This is nothing but the Green's function of the hyperbolic space of constant negative curvature minus a square. And this is for minus b square. So basically, if you have these conditions, the Green's function can be bounded from above and below by the fundamental solution of the hyperbolic Laplacian with the corresponding constant sectional curvature. Okay, so we prove this. Yeah. So after proving this theorem, we noticed that this part, that is the upper bound, this portion was already known way back in 1976 due to these people, and they used some probabilistic way to calculate the heat kernel, and they integrate over the time variable and to get this estimate. So, however, we prove this theorem using comparison theorem, using a more PDE or potential theory approach. Okay, and the crucial tools which we use are Hessian comparison theorem. I'm not going to the details of what it is. So that basically tells you that this kind of a function is going to be super harmonic away from the singularity. And then we use what's known as the Laplace comparison theorem in Riemannian geometry under the condition of the Ricci bounded from below to show that this quantity is going to be subharmonic. Okay, then you have to use some standard arguments in either in PDE or potential theory to get this kind of an estimate. That's how you prove it. Okay, so even though this part was known, the proof was different, but our proof is more natural. It's PDE or potential theoretic approach. Okay, so we have this estimate. And then moreover, we also have estimates for the gradient. So that is gradient of the Green's function, how it differs from that of the Euclidean term. We have an estimate like this. And once you have this, we can define the substitutes for the Rees potential in this case. So I will do, so the Km, the Green's function in the case of m is equal to 1, it is going to be the gradient of the Green's function. And m is equal to 2 is the Green's function itself. And then injectively, you can define for m even like this. For m odd, you can define like this. You can define like this. And then using that, you can prove some nice estimates on the symmetrization of these kernels. Some estimates like this. Okay. And you need a lot of estimates on the Green's function. Apart from whatever I have stated, you need more integral estimates, so on and so on, to prove these estimates. However, we could prove those estimates, and we could prove some estimates like this. And once you have such estimates, then you can put the Adams machinery to work, and you can prove the theorem. More precisely, Adams machinery has been refined, and it has been proved in a more general way, written in a more general way in metric spaces by Fontana and Morpurgo. It appeared in 2019, and we can directly use those theorems when you have this type of estimate to establish the Adams inequality. That is basically our proof. Okay, so I just end by just making one statement that when you come to Moser-Trödinger, that is when k is equal to 1, in fact, things are even better. You don't need this assumptions on the Ricci or on the sectional curvature. Without anything, you can have a Moser-Trödinger inequality in general Hadamard manifold. So it is this, there is no condition. The only thing is that you have this kind of a constraint, you have this kind of. Again, it is basically an approach using the potential method. The potential here is not the one which I have been talking about. It is the following, this kind of an estimate, which is quite common when you prove these inequalities in the Hadamard manifolds. You have this kind of an inequality, mod u less than or equal to 1 by omega n minus 1, integral omega, gradient divided by r to the power n minus 1, jx r theta. Okay, so I will tell you, and this quantity is nothing but is the volume element of the manifold written in the polar coordinate around x using the exponential chart. Okay, and then what comes to our rescue is that for this kind of a rescue thing, and there are some volume comparison theorems in Riemannian geometry, which tells you that this basically this Jx as a function of R is monotonically increasing. Okay, so that basically helps us to prove whatever job this O'Neill's lemma did in the previous case, and you can prove that. So when the Moser in the case of Moser Trudinger, you have a complete result. But in the Adams inequality, what we proved, we need the bound on sectional curvature and the Ricci curvature. Okay. So with that, I will stop here. And the reference, for example, so whatever result I talk about, so the details can be found here. So it's a paper, as I mentioned, with Jerome Bertrand and sharp Green's function estimates on Hadamard manifolds and Adams inequality. It's in IMRN to appear. And if you need more details about this Adams inequality and so on, so I have written a expository come little bit of a survey on this topic, and which recently appeared. And you can see this, and here it contains all the references, whatever I have talked about, and for more references and so on, you can see these expository articles. Okay, with this, I will stop here, and thank you for your attention.
Thank you very much, Sandeep, for such a lucid talk. Now we'd like to take questions and answer from the audiences. So, let me see. So we have a question from Himanshu Gupta. So he says, can you tell briefly about some physical examples where inequalities are applied?
Inequalities are applied.
Yeah, some physical examples where these inequalities are applied.
You see, for example, physical example, I mean, see, when you model it, it comes to a differential equation, right? For example, even when you talk about solving the Laplace equation, Laplacian of u is equal to f and u is equal to g on the boundary, then there is a energy method what you learn basically, right? For example, when you are trying to do that, you have to find a minimum of an energy function. Okay, so when you do that, you need estimates. Okay, so there, whatever inequality which you use, there is the Poincare inequality. And similarly, when you talk about the inequality equations like minus Laplacian of u is equal to f of u, or more precisely something like u to the power p, which comes in many applications, there you need to estimate u to the power p with this kind of an inequality. Okay, so now when you are talking about these kind of inequality, exponential inequality, one of the main things which I mentioned, which comes from while trying to solve this PDE, which prescribing the Gaussian curvatures, and there are other PDEs like the mean field equations and so on. Okay, and there these type of inequalities are used very much.
Okay, so our next question from Ramavat Omkar. Can we apply this method to perturbation technique, sir? So he says.
I have to understand what is perturbation techniques.
So I will try to unmute him and maybe he can ask the question if he is still listening. I'll try that. Ramanath Omkar. So I'll give you allowed to talk. So please ask the question directly. Hello, Ramanath Omkar. Ramavat Omkar. Can you hear us? So he can talk now. Ramavat Omkar. Okay, so maybe some technical thing. So we go to the next question. Once again, I unmute him, mute him. Okay, so the next question is from Mrinmoy Bishwas, and the question is very long. I will try to unmute him also, so that he can ask the question directly. Hello, Mrinmoy. Hello, Mrinmoy Bishwas. Hello, Mrinmoy Bishwas.
Maybe you can read. Well, let's see whether
Yeah.
we can make out what it is.
Yeah, okay. So he has two questions. Is the optimal value is achieved in any domain, say convex domain? Can we say something about this?
Optimal value of what? There were many inequalities which I stated.
I guess Moser, Trudinger, Adams. I don't know.
Yeah, Moser-Trudinger is well known, and so in any domain, in a bounded domain, it is attained, and unbounded domain you can't say. In fact, there are domains where it is not attained. Yeah.
Okay, so he has a very long question that I will read out. As you have started the topic with Sobolev inequality in Rn, but we see the Adams or Trudinger inequality in a domain with finite measure. So naturally, the question comes to my mind is there any version of Moser-Trudinger or Adams inequality in Rn or half spaces?
Yeah, it is there, and I think after he wrote the question, it was answered, right? So in some part of the talk, I mentioned that you change the right-hand side instead of gradient of u to the power n plus some lambda mod u to the power n. Okay, so there are, in fact, there are plenty of works, and if you need there's a lot of references given is in that survey paper which I mentioned or the expository article. In fact, there are plenty.
Okay, so I mean the question actually the thing doesn't finish it. So if yes, what is the base constant?
It's the Euclidean constant, the same.
Okay. Is there any, so the question from Minmay Bashwa still continues. Is there any development to this result for non-local cases?
Yes, there are.
There
And
are.
many of these potential approach, which I have been talking about, it can be used even in the case of a non-local case. There are many results.
Okay. Okay. Now there is a question. So these are, oh, Minmay Bashwa is again asking for Adams inequality.
Yeah, it is there.
It
Yeah.
is there.
Yeah,
Okay.
yeah. Even there
So,
is a paper of Fontana and Morpurgo, and they have been talking about this fractional weights. Those results are basically aimed at a fractional case. Okay. There
okay.
are results. There are many, in fact.
Okay. Now we have a question from Johannes Osborne. He says, thank you for your talk. You emphasized discrete gradient operator indexed by k dot can, indexed by k.
Yeah.
So you emphasized discrete gradient operator indexed by k. Can similar inequalities such as Adams or Sobolev be proved with some kind of fractional gradient operator in the upper bound?
No, there are fractional inequalities, but it may not be exactly defined that, right? So that's exactly was the previous question, right? So
Okay.
the fractional case, there are inequalities.
Okay. Okay. So the next question is from Shoykot Majumdar. Does similar result hold? Oh, one second. Does similar result hold only with only bounds on Ricci, and or in some cases only bounds on the scalar curvature?
Scalar curvature, I'm not sure.
Okay.
Yeah, so at least you see, at least the Moser-Trudinger tells you that Moser-Trudinger, whatever I stated in the end, which doesn't require even the Ricci. Okay, so it was just on any Riemannian manifold, the Hadamard manifold. Okay, so I don't know. Maybe there is a way to relax these conditions, but at least we were unable to do it. And basically, we needed some control over the volume, and that is where the Ricci is used. And when you are the scalar curvature, I don't know how to do it.
Okay, thank you. So there is a question from Vandana Sharma. How to figure out how much we need to truncate the exponential function? That is for what s that Adams inequality hold?
So how to figure out? You see, one way is to just look at, you see, I wrote an inequality, right? If that an inequality holds, that ES is greater than or equal to x to the power s by s factorial. Okay. So one way is to look at, for example, you can put, it will give you a Sobolev type inequalities, x to the power s P, etc. Okay. So what type of S you can have an inequality? And once you have that inequality, you can prove that. Okay. For example, so we had some results which I did not mention here, which tells you that in R2 or even in Rn, if you have the Poincare type inequalities, then you can immediately have the Moser-Trödinger or Adams. Or in other words, you have that lowest possible x to the power s by s factorial. If you have the control of that using the integral of the gradient, then you will be able to prove the higher inequalities. Okay. So that way you can detect what it is.
Okay. So we have a question from Dharmendra Kumar. So he says future research problem. So what are the future research problem?
See, there are many, like, can you remove those bounds? So that is something which I can talk about, which I am talking about, whatever I am talking about. Can you remove these restrictions? Okay. And there are various other things which people, and depends on what kind of problem you want to address. Okay. And another thing is, can you have inequalities with the different constraints? Okay. For example, the inequality, Adams inequality, which I talked about in the hyperbolic space, the result of me and Karmakar, and it was the constraint was using the Panit's operator. So one can look at whether there are results similar to that. And like that, you can think about various results. And also the ultimate aim is, the question is, you see, many of these things are motivated by the study of PDE to prescribing the Gaussian curvature or the corresponding length for the atoms, the question of Q curvature and so on, QK curvature. Okay. So can we use these inequalities, and whether you can study this question of prescribing the QK curvatures and so on. So that is the main aim. So there are many directions one can take forward.
Okay. So there is a question from Ajay Singh Parmar. So he says, can it help in the Leray-Wick solution of, I guess, Navier-Stokes equation of fluid flow or any other things?
I have no clue.
Okay. So let me see the, please, is there any other question? Let me figure out. I have to see the chat box. Okay, maybe there are, but there are many. I mean, so yeah. So thank you, Professor Sandeep, for such a lucid talk again, and thanks for answering the question and answer of our participants. Thank you very much. And for the participants, I would like to say that please write your please try to write the question answer not in the chat box but in the question answer part. Okay, and we hope to see you next Tuesday at 3 p.m. for Professor Zua's talk.
Hello, sir.
Hello.
Hello, sir. Kaushik.
Yes.
Sir, I could not write in the, since I'm in the panelist list, I could not write in the question answer section. So I'm asking it here.
Okay.
If that is okay. So I had a question. You once told that Poincare inequality does not hold in Rn. Poincare and Sublevel inequality, those inequalities do not hold in Rn. But
I told only Poincare.
Poincare, yes, yes.
No,
so
when that K into P equal to N, you cannot have the Sublevel.
Yes.
Yeah.
Yeah, but in if we take a manifold of negative curvature, we even if its measure is infinite, we can have Poincare inequality.
Yeah, but I have put a condition that sectional curvature is less than or equal to minus a square.
Yes, bounded.
Yeah.
It should be bounded away from zero. So, does this say anything about geometry of the manifold?
Can you make it more precise?
No, actually, the question itself is vague. There are other theorems on negative curvature manifold with similar restrictions, which say something about like the fundamental group of the manifold or things like this, geometry of the manifold. So what are the geometric implications of the fact that the inequality does not hold in Rn, but holds in manifolds with negative curvature?
See, I don't know. For me, it is more than the geometric, it is the spectral. So it's basically, for me, it tells you that the bottom of the spectrum is positive or there is a spectral gap. Okay. So that is the aspect I'm interested. And I don't know about the other implications.
Okay. That's all.
Okay. Okay.
Hello,
So,
sir.
yes.
Hello, sir. I am asking also a question since I am not writing in question and answer section. So, is there since Moser to Dinger inequality and Poincare inequality, they are equivalent, right?
Yeah,
for bounded.
yeah, domains we have proved. Yeah.
Yeah. So I saw a paper, your paper, which states that for a simply connected domain in R2,
Yeah.
the Moser-Tudinger and Poincare, they are equivalent by using some complex analysis, right?
Yeah. Yeah.
So is there any different proof for this?
Yes.
Without using complex analysis?
Yes. See,
Oh.
so there is the proof. You can see there was a paper of Gabriela Mangini and Luca.
No, but that was is basically Moser-Tudinger imply Poincare, but for simply connected domain, I need.
No, you mean Poincare implies is equivalent to Moser-Tudinger. It holds even in the higher dimensions.
Yes, yes.
Yeah. So it is there in that paper, and it doesn't use any complex analysis, just symmetrization. Basically, whatever we have been doing, and they adapt to that situation, and they prove some nice inequalities and proves it. Yeah. So it doesn't use any complex analysis.
Okay.
If you need a reference, you can see in that survey article whatever I mentioned. Yeah.
Okay.
Okay. Thank you so much again, Sandeep, for such a wonderful talk again. And